So section 5.2, we're going to look at some ways to actually calculate probabilities, and a lot of this will be familiar to you from previous math classes. All right, so one thing that we're going to start with is called a probability model. Okay, and so it has to contain two things. It has to have a list of all the possible outcomes, and that list is called a sample space. So, for example, if I was going to flip a coin, the possible outcomes are heads or tails. So that's my sample space, heads, tails. And then I need to have the probability for each outcome. So in that coin example, each outcome, heads and tails, has a probability of 1/2. All right, so this is an example of a probability model for rolling two dice, two six-sided dice. Okay, this is a list or picture of all of the possible outcomes that could happen. And then the second part that we need is that probability. So because for dice, each outcome is equally likely, we would say that each outcome has a probability of 1/36. So this would be a probability model, both the picture and the statement about the probabilities are required. All right, so an event in probability is any outcome that could happen. So we can define an event as anything we want as long as it is a possible outcome. All right, and so we're going to say that event A is getting a sum of 5 when two fair dice are rolled. Okay, so in that sample space, there were 4 different ways to get a sum of 5. So that means the probability of event A is 4/36. Okay, so written out in formula form, that's what it looks like. Again, this is like the very basic form of probability that you have probably seen before. Okay, so when we make our probability models, they are not valid unless all 4 of these things are true. Okay, the first is that we can do what we just did, which is find a probability by using that formula. The second is every event has to have a probability between 0 and 1. All right, so it's mathematically impossible to have a probability less than 0 or greater than 1. All of the possible outcomes together, the probabilities have to add up to 1. So if I take everything in the sample space, the probability of all of them together has to add up to 1. All right, and then the probability that an event does not occur is 1 minus the probability that it does occur. Okay, we call this the complement, and a lot of times you'll see it written like this, event A, and then we put a C up as where an exponent would be to say the probability that A does not happen. Okay, and that always has to be equal to 1 minus the probability that A does happen. All right, so let's look at an example. We have a bag of M&Ms, and we're just going to take out one of them. All right, and then the manufacturer gives this list of probabilities for getting each of the colors in a bag of M&Ms. So first we have to say, is this a valid probability model? Well, we're going to look at two things. One is, are all of those probabilities between 0 and 1? And the answer is yes. And then the second one is, do all the probabilities together add up to 1? Right? And the answer is yes for both of those. So we would say yes, this table right here is a valid probability model. All right, find the probability that you don't get a blue M&M. Okay, this is what we call the complement. All right, so the probability of not blue, or the complement of blue, is equal to 1 minus the probability of getting a blue M&M. And we take that straight from this chart. So 1 minus 0.207 equals 0.793. That's the probability that my M&M is not blue. All right, last question. What's the probability that you get an orange or a brown M&M? So either orange or brown, okay? When we are looking for two different events, and those events are what we call mutually exclusive. And two events are mutually exclusive if they cannot happen at the same time. So in this case, an orange M&M or a brown M&M, there are no M&Ms in that bag that are both brown and orange. Each one has just one color. So orange and brown are mutually exclusive. Okay, anytime we have mutually exclusive events, we can find the probability of one or both of them happening by just adding those two probabilities together. Okay, so the probability of orange or brown is equal to the probability of orange plus the probability of brown. We just add those two numbers together. Okay, important for you to note that this only works for mutually exclusive events, meaning things that cannot happen at the same time. There's no overlap between the two. All right, and so we'll look at what happens when events are not mutually exclusive in this next section. So when we talk about the word or, and we're just like in general in the English language, there's kind of two different ways that it can be used. So let's say that you go to Olive Garden and the waiter asks you if you want soup or salad. They're asking you to pick one or the other. You can't have both of them, okay? But let's say you get some coffee, all right, after your dinner, and they want to know if you want cream or sugar. You can have cream or sugar or both of them. Okay, so even though it's the same kind of thing, soup or salad, cream or sugar, we kind of understand in English that there's two different ways to use that word. Okay, so in statistics, when we use the word or, we're talking about the coffee kind. Okay, it could be one or the other or both of them. All right. So one of the ways that, because that math can get confusing, sometimes it's easier to look at things in a two-way table, all right? And so we've seen these in an earlier chapter. And so we've done these kind of frequencies before. So we have some data on gender and whether or not people have their ears pierced. Okay, so we're going to look at two events. Event A is the student being male, and then event B is them having a pierced ear. So find the probability of B. Find the probability that someone has a pierced ear. So I'm just looking at the yes column. All right, 103 of the 178 people have their ears pierced. All right, so I can either leave that as a fraction or we can turn it into a decimal and say that proportion is 0.579. Okay, find the probability of A and B. So now we want someone that is both A, which is male, and B has their ear pierced. Okay, so now I'm looking at just this box, the overlap between male. Okay, so male has their ears pierced. Where is that overlap? It's this box right here. Okay, so 19 out of 178 people in the class are both male and have a pierced ear. All right, and if we interpret that in context, because we're talking about a college class that this data came from, we would say there's about an 11% chance that a randomly selected student from this class is male and has a pierced ear. Okay, so we're not going to say A and B. We're always going to refer to the context of the problem. All right, and then the last one, and this is one where the reason that we want to look at these two-way tables. So if I say the probability of A or B, well, A is getting a male student. All right, so that'd be any of one in this column, and that's 90 people. And B would be anybody with a pierced ear, so that's this row, so that's 103. Okay, so when we did our OR probabilities before, we simply added those probabilities together. So 103 plus 90, and we put that over the 178 total. Okay, but there's an issue here. We have 19 people that are counted as both 100 out of the 103 people that have their ear pierced and the 90 people that are male. Okay, so the general addition rule, okay, we have probability of A plus probability of B minus the probability of A and B. So this is when events are not mutually exclusive. Okay, so when they were mutually exclusive, like in our M&M example, we can just add them together. But when they're not, we have to subtract the overlap, okay, the place where those two things overlap. All right, so it is 90 plus 103, but we have to subtract 19 out of there so that we don't count those 19 students twice. Then the last way of looking at probability that we're going to talk about in this section is Venn diagrams. So you might remember doing this in geometry. And so we're always going to start with a rectangle, and then we could draw different circles, maybe overlapping, maybe not, depending on how many events we're talking about and what are the probabilities of those things happening. So let's look at an example. All right. We have a survey where 68% use Facebook, 28% use Instagram, and 25% do both. And so we want to make a Venn diagram for this event. So I'm going to start with a big rectangle. This is my sample space. Everything, all the probabilities inside this sample space have to add up to 1. Okay, I have 2 events. I have event F, someone uses Facebook, and event I, someone uses Instagram. I also know that 25% of the people do both of these things. So I know that these 2 circles are going to overlap each other. And then we can start filling in some probabilities in our diagram. All right, 25% do both. So the intersection between those 2 circles has to equal 25. All right, I added some color so that we can make this a little bit easier to see, okay? 68% of the residents use Facebook. That means my blue circle has to equal 68%. I already have 25 in the overlap. So that means out here, it's gonna be 68 minus 25, okay? Or 43%, because my blue circle together has to add up to 68. My yellow circle is Instagram users. 28% use Instagram. So I already have 25 in this overlap. So that means all that's left out here is 0.03. Okay, now if we add these numbers together, 0.43 plus 0.25 plus 0.03, they do not add up to 1, and everything in my sample space has to add up to 1. So the group that we're missing is the group that doesn't use any of these. They don't use Facebook, they don't use Instagram. So that means in this space out here, I need to do 1 minus 0.43 minus 0.25 minus 0.03 to know the leftover. And so 29% of people don't use either social media site. Okay, so remember when you draw the rectangle, everything in the rectangle has to add up to 1. All right, so some different possibilities that we could have for Venn diagrams. Okay, remember the probability is inside the circle, which means that the complement is outside of the circle, because those 2 things would add up to 1. Okay, when we have overlapping circles, the intersection, the place where those 2 things cross, that is, we write that as A intersection B. You could also say it as the probability of A and B. Okay, we also have what's called the union. That would be A or B. Okay, so A by itself, B by itself, or the overlap. Right, and so a lot of times you will see these symbols used instead of the words and or. Okay, so this one that goes down is and, this one that goes up is or. A little hint for remembering those things is the union, and that symbol looks like a U. And then we have the intersection, and intersection has an N right at the beginning, okay? So that's kind of a way to remember what symbol means what. And then that's it for 5.2.